Welcome all to the Science-O-Rama Show, a weekly show featuring your chemistry questions. Alright folks, in today's chemistry episode, we will be discussing the much requested topic, equilibrium. So, to begin with, what exactly is equilibrium, you ask? Well, it's simple, because we love to balance a lot, and balance can be observed so much of it all around us in the world, in nature, and it kind of seems that everything is always trying to maintain this balance one way or another. We can go closer and just think of it in our daily lives as well. Think about how all the important work-life balance we're always hearing about, going on a seesaw, for example, or even much closer, as I said, our own bodies, and how our own bodies work in trying to achieve equilibrium or balance, because too much of anything is not good, and vice versa. One of the things that I believe is really important when studying chemistry, or any subject for that matter, is to try and create little examples or like monikers or something, which you could kind of relate to or remember when you're studying a new topic. And one of the things which I thought about when studying equilibrium was trying to think of it as balance, okay? So I've already mentioned balance, and we know that that's what equilibrium is. But one of the things which I pictured was the ancient Chinese philosophy symbol was the yin and yang. And the yin and yang, it symbolizes two separate forces or beings which are complete opposite of each other, kind of living or interacting with each other and maintaining this balance. Too much of yin is not good, and too much of yang would throw out this balance. And these separate and non-identical forces, they work together, and they represent much more philosophically, and also you could think about it, as I said before, in the real life, our world, and in chemistry as well. Alright, so now that that's out of the way and you kind of have a general idea of equilibrium and its definition, let's talk about how exactly is equilibrium achieved in a system. And one of the things which we can do first of all is just simply define equilibrium. So when you do a quick Google search, equilibrium is defined from Chemistry Libre text as chemical equilibrium is a state in which the rate of the forward reaction equals the rate of the backward reaction. In other words, there is no net change in concentration of reactants and products. Okay, all right. So this definition, it makes sense to me. But one of the things which I just wanted to clear up is we know what is a reactant. So in a chemistry equation or a chemistry reaction, which we would then form equations from, we know that we would have reactants and then we would have products which are formed by a reaction that would occur. And one of the things which is interesting when reading this definition is, wait a minute, hold on a minute. Chemistry reactions can go backwards? Yes, they can. And that was the things which kind of stood out to me before studying this unit. So the thing is that chemistry reactions are able to go backwards, and they could, which is defined here as reverse, or they could move forwards. Now, in a chemical reaction, as I stated before, the equilibrium is achieved by shifting or movement. And this is explained by Le Chatelier's principle, which states that if a change occurs in a system that's at equilibrium, or if it's disturbed, the system will then attempt to balance out or offset the change by shifting in either left or the right direction. Now, the direction of movement itself depends on the reaction and other factors, such as the change itself. Alright, so now that's enough of the definitions for now, and let's actually kind of see Le Chatelier's principle in action, and how we can kind of predict the shift and the movement and the change of reactions that are at equilibrium. Let's start off with this reaction. We would have nitrogen gas reacting with hydrogen gas to produce ammonia gas. We can just simply identify, we know that N2 and H2 are our reactants, and we know that the product that is produced here is NH3 or ammonium. So let's try and use Le Chatelier's principle, and I'll just make a little table right here on the screen. So for example, if I added some N2 or nitrogen to the mix, what would happen? All right, so the reaction, because we know that it's already at equilibrium, it would then shift away from the substance. So in this case, it's nitrogen, and it would then move to the right. And this is because, as I said before, we're shifting away. And this is because the extra concentration that's there now, it's present, it needs to be used up, so it will create more product as a result. So the same thing that would happen if you added more hydrogen. So H2, you increase the concentration of the amount of hydrogen present. The reaction that's at equilibrium will move away from the hydrogen or away from the substance. And why? Extra concentration needs to be used up again. So the same thing that's going to occur for both reactants. Now, let's think about if we decrease the concentration of the substances. So for example, if I removed an N2, so if I removed a nitrogen, what would happen is that the equation would then shift to the left and towards the actual substance. And why does this happen? This happens because the reaction would then need to produce more of the nitrogen in order to make up for what was reduced. So it would shift to the left. And now the same thing that would happen for the hydrogen molecule. So if you had decreased the concentration of hydrogen, it will then shift towards the left because we want to have more of the substance that's going to be made up for what was removed. Now let's move on and look at adding and removing some of the product. So same thing happens here. If I was to add or increase the concentration of the number of ammonia molecules, then what would happen is that the reaction that's at equilibrium would shift to the left. And this is away from the product away from the product, yes, or the substance, and towards the actual reactants. And this for the same reason as I mentioned before for the reactants of nitrogen and hydrogen. Now, if we had removed some ammonia or removed the concentration of ammonia in the reaction, it would then shift to the it would then shift to the right. And for the same reasons as I mentioned before, we are removing a product and it kind of wants to replace it instead. Let's try and think about what would happen if we kind of mess around with the external factors of this reaction. So what I mean by this is kind of increasing the temperature or like the volume or So let's first put this out there that this reaction is an exothermic reaction because it has an enthalpy of negative 92.4 kilojoules per mole. So we know that it's an exothermic reaction, and this means that heat is produced. All right, so if we were to, for example, increase the temperature, which when you're increasing the temperature, you're in fact adding heat or energy, what would happen is that the reaction would then shift to the left. Why is that? So this means because if heat is added and heat is produced, and we know that the heat produced, it's on the product side, and this is on the right, what would happen is it would shift to the left because it's moving away from the heat, and this is because the extra heat or energy, it needs to be used up. Now, if the opposite happens, it will be the opposite reaction, an equilibrium reaction occurring. If you were to decrease the temperature of the system, what would happen is it would then move to the right, because this is then going to be we want the energy to be produced. We need this energy to be made up or produced in order to kind of make up for the loss that was present when you decrease the temperature. Moving on, if you were to increase the volume, which in fact you're going to decrease the pressure when you increase volume, what would happen is that the equation would either shift to the right or the left, depending on the number of moles. So, for example, if we ended up increasing the volume of the container, what would happen is that the reaction at equilibrium would actually move towards the side with the greater number of moles of gas. And why does this happen? So this happens because when you're increasing the volume of a container, you are actually decreasing the pressure. And when you decrease the pressure, then the reaction is going to try to offset this change and maintain its balance by kind of alleviating this loss of pressure and moving towards the side with the greater moles of gas. And this helps to maintain the equilibrium. Let's try to predict the volume change in our previous reaction. You would see that on the left side, we have 1 mole of nitrogen and 3 moles of hydrogen, which gives us 4 total moles of gas on that side, on the left. And on the right side, we only have 2 moles of ammonia gas. So we can tell that the side with more moles of gas is going to be the left side. Therefore, at equilibrium, this reaction would shift to the left if disturbed or if there was a change. Now, for the opposite or vice versa, if you were to decrease the volume, you're going to in fact be increasing the pressure that's present in the system. And if you're increasing the pressure in the system, at equilibrium would then shift towards the side which has the fewer number of moles of gas present. So we got to remember, of course, as I mentioned before, increasing the pressure means that you're decreasing the volume. So let's look back at our equation, and we can see that by decreasing the volume or increasing the pressure, that this reaction would then shift to the right side. Why is that? Because there's less moles, as I mentioned, of ammonia gas present in this equation. So there's 2 moles and versus 4 moles on the reactants and 2 only on the product side. Okay, so moving on, let's discuss what would happen according to Chatelier's principle if we were in fact to add a catalyst or like another element into the reaction. And which way would it shift, right or left? Think about it. Well, the answer is no, nothing would happen. There would be no shift like in the way that we're describing for the previous examples if you were to increase the concentration or the pressure or volume, etc. Now, there would be no shift in the equilibrium, and this is because that the rates of both the forward and reverse reactions are increased by the same amount. So when you're thinking about this, using Le Chatelier's principle, there would be no shift, and we would not be able to say that it would shift right or left because it wouldn't. However, it should be noted that there would be no change in the position of equilibrium. However, the time that it takes to reach equilibrium would decrease if a catalyst was added. Alrighty, so now that we've got all of the definitions and kind of the learning stuff out of the way, let's put our knowledge to the test and kind of describe more real-life experiences and how equilibrium will affect these relationships and the reactions. Now, I have 2 examples in which we can put our knowledge of equilibrium to the test. The first would be the relationship between Le Chatelier's principle, the pH scale, and in relation to the dental caries or dental cavities, as well as fluoride, and basically the principle of equilibrium and how all of these factors can be represented in a reaction. For starters, we know that tooth and bones in our bodies, specifically if we're talking about the tooth, we know that it's got a tooth enamel, and this tooth enamel, it's made up of this mineral called hydroxyapatite. I'm not sure if I'm saying that right. So anyways, we know that we have the hydroxyapatite, and basically what happens if someone has a cavity, or if they begin to develop a cavity, they develop this cavity when bacteria eats the carbohydrates from the foods that you ingest. So this could be sugary foods or just simple like carbohydrates like bread or pasta or stuff like that. And this would then produce an acid that would work on attacking or like penetrating the enamel on the tooth. And you would then have the calcium phosphate that to be destroyed from the tooth enamel, and these acids that destroy, they change the pH, so this is when demineralization begins to occur. Now, after doing a bit of research, I kind of learned about the process of remineralization and demineralization, both natural processes that occur within, like for example, if we're talking about within dental cavities and our teeth. So these 2 processes are very different, but they are opposite, and they are in an equilibrium. Of course, like the name suggests, demineralization is removing the minerals from the tooth enamel, and remineralization is adding this minerals to the tooth enamel. minerals that are lost from demineralization, then remineralization would occur. So a tooth would need to be remineralized. And how does fluoride come into this? Well, fluoride creates fluoridated hydroxyapatite, which, according to the Dimensions of Dental Hygiene article, the enamel of the tooth dissolves when fluoride is undersaturated. So if it is saturated, it is at equilibrium. And what happens is that the fluoride ion would then take over the hydroxy ion. What would happen is that we would then have this substance or this mineral called fluorapatite. And fluorapatite is stronger than hydroxyapatite, and it is able to basically coat the tooth enamel and protect it and basically remineralize it from the previous damage that had occurred. In discussing the equilibrium between calcium and phosphate ions, as well as the tooth enamel, we need to realize that when the pH level reduces or drops, basically, this would mean that there would be a dissolution of the tooth mineral, which, as I mentioned before, is hydroxyapatite, and this demineralization would reduce the natural capacity of the saliva, and the saliva would then work on increasing the pH minerals and trying to place those minerals back into the tooth. And this process is basically what the entire equilibrium process that I'm describing right now of a tooth, and how fluoride gets into this mix is fluoride basically just increases the pace of this process. So it makes the reaction occur much faster, and it reduces the cavity risk of occurring and can also reverse the effects by just simply increasing the remineralization process and decreasing the rates of demineralization that occurs. And as stated before, what happens when fluoride is present in a tooth that has dental cavities, or in order to do this prevention or reversal of effects, is that the fluoride ions, so the F minus, would replace the hydroxyl groups, creating new bonds and forming the substance fluoroxyapatite. Mentioned before, fluoride gets right to work, and basically it protects the teeth against acid and like the erosion that occurs with acid within the tooth enamels by basically, as I mentioned before, replacing the hydroxide with a fluoride ion. Important concept that we got to kind of realize or understand when kind of studying the relationship between dental cavities and fluoride and the basic equilibrium that occurs is also another concept called the critical pH. The critical pH is basically just like it's a solution, and it's a saturation compared to like the minerals within the enamel. And with this critical pH, we can basically look at the levels that it's there and make some assumptions. So, for example, if the acid level that's present in the enamel is greater than the critical pH value, then this is considered generally safe. However, if the acid levels are lower than the pH, then this is when the teeth start dissolving. And saturation in this case would mean that compared to the mineral, that more of the solution would then precipitate. And basically, when you have like undersaturation occurring, then the teeth would begin to dissolve, like the tooth enamels. And this is when cavities, as I mentioned before, would start to occur when the tooth is dissolving. And moving on and thinking about Le Chatelier's principle in connection to this occurrence is that basically the solubility of the enamel is one of the big important factors here. And you would need to know that the solubility of the enamel, it would increase if more hydroxide ions are actually consumed, and this would then make the forward reaction become more favored, and the reaction would be more likely to move in the forwards direction. And so basically this is one of the main aspects to kind of take away from the whole explanation that I tried to give out. So of course you need to remember solubility, critical pH, and like all of these, they all work together in just understanding the basic concept that's explained by Le Chatelier, and that is that by having the solubility, more hydroxide ions consumed, then it's going to move more in the forwards direction, and this is good for the teeth. Hopefully, after listening to this explanation, you now have an idea of basic equilibrium systems, some of the terminology, some of the workings of how and why this would occur, and as well as an understanding of reactants and products in a more realistic and real world example. So this is an example is one that I've kind of been working on throughout the unit, and it's one that I've pretty much researched a little bit about, and it's basically about homeostasis. And homeostasis is basically similar to the dental cavities and fluoride discussion. Homeostasis is also a sort of equilibrium that occurs within our bodies, and when homeostasis occurs, this is basically it's like a natural function that occurs, and it involves much more than like a single part in our body, but it's basically like the entire and it's like our entire body. So just to kind of give an example of this and to talk about it more, when I searched up homeostasis, and I got like a definition, and I'll just put it up here. So homeostasis is defined as the goal of living things trying to maintain homeostasis, which is basically a dynamic equilibrium, health, and internal balance. So all life functions interact in order to maintain this homeostasis. So in our own bodies, as I was mentioning, we could have some examples. For example, how can you maintain homeostasis? So one of the things that you could do is, well, not you're doing it, but your body is doing it, is the maintaining your internal body temperature. For example, human beings, we have a natural body temperature of 36.5 to 37.5 degrees Celsius. And if your body temperature is even a little bit greater than this or a little bit less than this, if you have a little bit greater, we know this as a fever, and this could potentially point to other signs of dysfunction within the body, such as you having a flu or like a cold, or like something's going on and your body's fighting in order to eliminate this threat. But the thing that you should understand with the body temperature is that it's a process, and that our bodies have this process. It's called thermoregulation. So thermoregulation is basically the process that allows our bodies to maintain it's like basic internal temperature, which I just mentioned before. So thermoregulation, it works by having internal body temperature basically being monitored and checked by our brain, and this part of the brain is called the hypothalamus. So the hypothalamus, one of its functions is also to kind of maintain and check the body temperatures, and if the body temperature is a little bit over or it's a little bit under, then what happens are various functions that which our body could use. For example, one of the common ones would be when it's really hot, your body would maintain its internal temperatures by sweating. And sweating, it's basically evaporates, like the liquid evaporates, and it cools your skin. Another opposite effect slash function would be if your body is too cold, your internal temperature is too cold, then your hypothalamus would then send a signal which would make you shiver, for example, if you're too cold, and this is in an attempt to kind of create warmth. And another cool thing that I found when researching about this topic and homeostasis and equilibrium is that basically you could equilibrium and homeostasis. So homeostasis is basically the tendency of the body to kind of try and achieve or maintain this equilibrium, while equilibrium is actually the body's kind of reaction or response in order to, as I said, maintain this set equilibrium or balance. When we're talking about equilibrium, there's a lot of things between homeostasis which could kind of cause a homeostasis imbalance. It's a new word that I've learned. And homeostasis imbalance, it could be caused by a variety or number of various aspects or factors. One of the things which you could discuss might be in simple things such as genetics. So you could have a genetic imbalance which might affect the homeostasis of your entire body, or if you have, for example, you're taking external influences, or such as if it was a lack of physical activity, this might reduce the amount of a certain vitamin that you're being exposed to, or some sort of energy that you would have. based on certain factors like this. Or another thing which could be affect that I did not know and that was pretty interesting is your own mental health. This could actually have an effect on your homeostasis or equilibrium of your own body. Of course, drug and alcohol abuse would also affect the homeostasis, and also nutrition deficiencies is another big one that I found when researching this topic. Another factor that could cause homeostatic imbalance is actually your own environmental influences. So the environmental influences is actually an interesting one for me personally, because I remember doing a research project not too long ago for another class, and it was basically on the environmental influences or that such as toxins, for example, when it had affected a community's water supply, and the mental aspects and the physical health, wellness, and a lot of other issues that had occurred due to this lack of imbalance and this harmful toxin that was present that was not really supposed to be there. Now, throughout this unit, it's really been great fun researching and learning about all of the different systems, the different factors, and a whole lot of real-life examples as well that occur like just within us, like our own bodies. It was pretty interesting. And if there's one thing that you should take away from this presentation is basically just knowing that equilibrium is all about balance and that an equilibrium system can be found pretty much anywhere. I mean, when I was brainstorming the topics of of my personal example that I should use from the unit, I was thinking of a whole lot of stuff, from just a simple seesaw to the complex homeostasis system that I had described. In the end, I hope that you at least learned the importance of equilibrium and a whole lot of other topics such as the reactants, the product, the Chatelier's principle, how the reactions would shift, and a whole bunch of other stuff. Taking the time to really learn more about our surroundings and the different systems has really been a great deal of fun for me, and I hope you enjoyed as well. Thanks. Bye.